Hello everyone, welcome back to Power System ECE360 class number 11. Today we're going to talk about capacitance of the line. So capacitance is capacity to hold charges per unit voltage right here, C equal to Q over V. If we use this equation to develop the line to line capacitance, we'll get the equation right here. All right, so where is this? So it's line to line capacitance, line 1 to line 2, between capacitance between them. That means your line 1 here, line 2 here. So 1 and 2, so capacitance in between the line, that's C12, right? And it depends on epsilon 0, which is permittivity of the dielectric materials, and distance between the line from here to here is D, right? And R, this is not, remember that in inductance we have ds, right, for inductance, which is geometric mean, self-geometric mean radius of the conductor. But here we use R, only radius, not the geometric mean radius. We use the radius, actual radius for capacitance. So there's a big change from inductance. So this is actual radius, not R prime. It's not R prime or ds, is R for capacitance. There's a difference over here. And you get the Faraday per meter. So now let me explain something over here. So if you have the capacitance line to line, if you have a neutral between the line, then you have the capacitance from 1 to neutral is C, 2 to neutral is C, both the same. Then what is C12? C1 is the equivalent capacitance of this 2C, right? So we know that is for capacitance, this is the series connection over here, that will give you C2 inverse. That means C12 especially half C, right? So C12 is half C. That means so C is 2 times of C12. So C is 2 times of C12. So if I go back to the last equation over here, where we found C12, if I want to find C, which is line to neutral capacitance, so C is line to neutral capacitance, that would be 2 times pi epsilon 0 over natural logarithm d over r. So this is the line to neutral capacitance. So line to neutral, right? So and this is line to line. So there's two capacitance here. One is line to line, one is line to neutral. Again, for the asymmetric line, we use GMD. So GMD would be geometry mean distance between lines over here. Then we're using R. Remember that we don't use what do you call it, DS or self GMR. For the conductor we use R here. So C, if you modify this, C over here, that is right here for microfarad over kilometers. All right, that's the modification for capacitance in microfarad per kilometer. Again, for the bundle over here, again, it's RB, right? We use RB here. So for 2 conductor, this is the RB over here. Remember, when say we do not using DS, we're using R. And for 3 conductor, this is the equation. You have 4 conductor. This is the equation. The only difference here, DS is replaced by R, and DSB is replaced by RB. This is the difference between inductance and capacitance. And same thing over here. Look at that, your RA, RB, RC. Those are actually, before this were DS and so on, they're replaced by your R over here. So earth effect on capacitance, this is the equation to see what the earth effect on capacitance over here. If your distance, your let's say distance from earth to the line is higher than distance between them, all right? So then this will become 0. Why is that? Transmission line is high enough, so that means these values and these values over here, H1, 2, H2, 3, 1, 3, geometric mean of that and geometric mean of that should be equal to 1. If that happen, this will become ln 1 and it should be equal to 0. So then only have this over here. That is the what we have in the previous equation, right? So that means if your transmission line is tall enough and high enough from the ground, you can ignore the ground effect in capacitance. All right, and we're going to do this problem in the class. And one other thing I want to mention in the capacitance is the charging capacitance. So what is current? Charging current is, okay, let me draw a transmission line over here. If you have a transmission line, let's say 3-phase transmission line, right? So this 3-phase transmission line, let's say phase A, phase B, phase C, and there's a ground, so neutral over here, say neutral over here, right? So then all the transmission line has a capacitance to the neutral, and this one also has a capacitance to the neutral over here. Let me go through this. And this one has a capacitance to the neutral, right? So these are all the capacitance to the neutral, right? So then let's say it's all C over here, all C, right? So then if you don't have any load connected over here, and or load current doesn't matter connected or not, so let's say it's no load, then from the line A, let's say this line A, there should be a current going through. Let me take a different color here to illustrate. So there'll be a current, no matter what load connected, there's a current going through the capacitance to the neutral, right? This is the current right here. Okay, and same thing happened. There's also capacitance between line to line because of the voltage difference between line to line. There's also can be capacitance, as I showed before. There's line to line capacitance here, line to line capacitance here, line to line capacitance here, right? So then this is the line to line charging current. This is the line to neutral charging current right here. So this, look at here, this over here is the current. No matter your load is connected or not, there's a current going through the capacitance. What it's doing is basically charging the capacitance. That's what we call charging current. This, no matter what, is charging capacitance. You're losing current to the capacitance, to the neutral, who is basically charging the capacitance. So that, due to that charging current, it depends on the capacitance value and the line to neutral voltage. If voltage is higher, all right, you'll have more capacitance. Sorry, more charging current. If your capacitance is higher, you get more charging current. Your capacitance gets higher. If you go back over here, let me show you this equation right here. Your capacitance would be higher when you have GMD is low. If your GMD is low, that means your conductors are close to each other. You have high capacitance, right? So when you have a cable line underground, you're all three conductors under one cable, right? So they have your GMD between the line is very small, then you have high capacitance. That high capacitance will cost you high charging current. That means you cannot go further. Before you go to the load, your all the current would be lost into the charging capacitance. That's the problem with the underground AC line. So when you have, let's say you have a DC line now. You have a DC line now. In DC line, your frequency is 0, that means omega is 0. So there is no charging current. So if you go underground, it's better to go with the DC line because DC line doesn't have any charging current because capacitance is 0. Frequency is 0. That will make your charging current is 0. So that's why underground line, mostly DC, preferable for long distance, no AC. We're gonna talk about this example over here. Then there's some effect of transmission line here. If your height of the conductor is large as compared to the distance between them, you can ignore the earth effect. We'll talk about that. And magnetic fields, if your transmission line is carrying time-varying signals, it will induce voltage to the nearby conductor. If you have a long enough conductor, you have a voltage induced in the conductor. If you have voltage induced, you can have current in there too. So that's why your fans or any other long conductor close to transmission line could have induced voltage and current in there. All right, and also that can also have an interference with telephone wires if it's close by and to the transmission line. And if your transmission line has very high voltage and have kind of like moisture around it, it can break the molecules and ionize them close to the conductor, and it can have a hissing sound around it. So that is called corona. All right. If it's corona high enough to break the total dielectric media between the lines, you can have a short circuit in there too. So there's a like dielectric strand of air, dry air, is 30 kilovolt per centimeter. If your voltage of the transmission line is higher than this gradient over here, it could break the dielectric media between the line. And you can power loss could happen because you can have a short circuit there, and you could also see the hissing sound, and also this can make the radio to be interference if they're close by to one another. That's all for capacitance, and I'll see you all in the class to solve the problem.